All right, everyone. Hello again. This is going to be part 2 of the chemistry fundamentals notes. So this is largely going to be about how to name various types of compounds, how to write those formulas, and how to draw some of them. So if you took regular chem, you already are somewhat familiar with how to name ionic compounds, covalent molecules, and acids/bases. Hydrocarbons, which we'll get to in a little bit, are going to be a little bit more foreign to you, but I promise it's not as hard as it seems. So starting with ionic type compounds, because we know that ionic compounds are going to be a bond forming between a metal and a non-metal. If you are dealing with one of those types, the non-metal is generally going to go second, and you are going to cross off the suffix to that non-metal and replace it with IDE. A metal is going to go first, and it is going to keep its name. But remember, if it's a transition metal, which is groups number 3 to 12 on the periodic table, it also is going to get a Roman numeral, which is going to denote that metal's charge in that particular compound. Okay. So there are some elements that you will run across that when the compounds are named, their names don't exactly match what they are, at least not in the English language. So an example of what I'm talking about would be a compound containing copper. Let's say copper sulfide. So you could name it copper sulfide, or you could name it cuprous sulfide or cupric sulfide or something like that, because cuprous and cupric both mean copper, but they mean copper of a different charge. So for example, copper 1, and that's copper with a charge of +1, could also be called cuprous, that suffix OUS denoting that charge. Or you could have copper 2, which is also named cupric, because that charge of +2 is denoted by that suffix IC. Okay. So what this table is general elements that have different names, but also elements that you will see transition metals having different charges. So these are going to be the most common charges you'll see of each of these elements. So iron could be iron 2 or iron 3 most commonly, ferrous or ferric. Now, I know that you're probably wondering, well, that OUS up here meant a +1, but down here it means a +2. I know. That's because the OUS versus IC ending doesn't necessarily mean one specific charge, but when you see the OUS, that's going to be a charge of less magnitude than the IC. Okay, so you'll notice all down here that when you see a charge of a lesser magnitude, like 2, that's going to be an OUS ending, or 1 up here. If you see a charge of a higher magnitude, like 4 or 3 potentially in some cases, you're going to see that IC suffix. Okay, so this is going to be a useful chart for you to reference periodically, because a lot of us probably didn't know that stannous or stannic referred to tin, because tin shares 0 letters with those names, or plumbous, plumbic referring to lead, because again, those roots come from a different language than we currently speak. So if you're going to name binary ionic compounds, and again, that's metal with a non-metal, we are going to have to swap, drop, and reduce if we're making the formula, or do the opposite of that if we're attempting to figure out the name. So looking at this example right here, we have magnesium and we have nitrogen. If you look at the periodic table, magnesium is in group 2, meaning it has a +2 charge. Nitrogen is in group 15, which means it has a -3 charge. And if you forgot why that is, there are certain elements, groups 1, 2, 13, 14, 15, 16, 17, and 18, that have definite charges in ionic form. Okay, so if we are going to swap and drop and make this compound, we're going to take this 2 and we're going to move it down and over, and we're going to take that 3 and we're going to move it down and over. Please note that I am not moving the positive or the negative with it. It's quite literally just the number. So our compound ends up being Mg3N2. And as for the reason that that is, it's because these atoms, these ions, are trying to make neutral compounds. So if magnesium is a +2, it's going to take 3 +2s to neutralize 2 -3s, because if we add all those, that's +6, and if we add those together, that's -6, which will cancel each other out. So that's why swap and drop works. Okay. So once again, we're going to end up with Mg3N2 as our compound. If we are bonding iodine and cadmium, on the other hand, we are going to have to do a little bit of looking into that. So iodine is in group 17, which means it has a charge of -1. Cadmium, on the other hand, is going to be a transition metal. So you'll notice that generally with transition metals, if you're going to take the name and make a compound, you need to know what charge that transition metal has. And I didn't give you that information. So it's actually, without me telling you more information, it's impossible for you to make that compound. So this one was a little bit of a trick question. But let's say that cadmium had a +2 charge, or it's cadmium 2 iodide. Okay. So in that case, we take our symbol for cadmium, which is Cd, and we give it a +2. We swap and drop, so we get Cd1I2. And if it's a 1, that's implied. So our final compound becomes CdI2. This here, number 3, says tin 2, or stannous fluoride. So stannous, remember, that is going to indicate that we have a compound containing tin, and that OUS ending means that it's the charge of a lesser magnitude for tin, indicating a +2. So we take our symbol for tin, which is SN, and we give it that +2 charge. We take fluorine, which is a -1 because of its group. We swap, we drop, and we end up with SNF2. 4 and 6 are going to prompt you to do the opposite. We're going to take our formula and we're going to get the name. So we have 2 elements here, Cr and I, which are going to be chromium and iodine. So we know that chromium iodide is the base name for this compound. So named because iodine, I crossed off that suffix and replaced it with IDE. Chromium kept its name, but there's one thing that's missing. Chromium's a transition metal, so we have to include a Roman numeral. So here's how we figure it out. Cri3 has already been swapped and dropped. So if we do the opposite, and that's an implied 1, we know that chromium had to be a +3 to begin with, which means it gets that Roman numeral of 3. Okay, ferric oxide is going to be iron and oxygen. Oxygen, because of its group number, we know is a -2. And iron, on the other hand, we should probably, if we can't remember what that IC ending means, we go back 1, right? Oops, I went forward on accident. We go back 1 and we consult our chart. We see that that IC ending means a +3. So we're going to go back here and we're going to give iron a +3 and we're going to swap and drop. So that ends up being Fe2O3. And then last but not least, we have CO and S. And so that's going to be cobalt and sulfur. So cobalt is going to keep its name. Sulfur is going to become sulfide. And cobalt, once again, is a transition metal. Sulfur is a -2, which we know based on its group. And if it's going to take 1 cobalt to cancel out 1 sulfur, we know that that cobalt is going to be a +2. Okay. All right. Again, that's a lot. But in class, we're going to make some cheat sheets to remind ourselves of the rules. Okay. Go ahead and move on to naming polyatomic oxyanions. So our example for this is going to use chlorine. And this is a little bit of a rehash of some things that we've touched on already. So when I had you learn some of the polyatomic ions, I gave you a trend to pay attention to, and that is that polyatomics with the suffix of ate tend to have more oxygens than those that have the suffix of ite. So anything that has an ite on it is going to have less oxygen, and anything with an ate on it is going to have more oxygens. Okay. But there is another trend as well. So these two both have ate, but they have a different number of oxygens. The difference is ClO4 has a prefix on it, per. So a prefix of per combined with a suffix of ate means even more oxygens, evidently. So then if it doesn't have a prefix, like this situation right here, there's still like a high number of oxygens, but not as many as if it had that prefix. And then down here, we see two suffixes of ite, but one of them has a prefix of hypo. And you'll notice that the one that has the prefix has even less oxygens than the one that didn't. So really, we're talking about a range with the most oxygens being per and ate, and the least oxygens being hypo and ite. So you'll see a number of polyatomic ions follow that pattern. So look out for it is basically what I'm telling you. But again, we're going to have a cheat sheet in class that we're going to make for that. Naming acids. So another thing that we went over last year, if you took chemistry with either me or Miss Mannering last year, but whoops, went too far again. But how this works depends on what is in the compound. So if your anion ends with IDE, so that's going to be basically any anion on the periodic table: nitride, oxide, fluoride, chloride, bromide, any of those. Your acid is going to have a prefix of hydro and a suffix of IC. So hydrogen bonded to chloride, again, chlorine found on the periodic table, becomes hydrochloric acid. So you're again seeing that prefix hydro and that suffix of IC replacing the IDE. If, however, you are dealing with an acid that has a polyatomic ion that ends with ate, so for example, carbonate, which is CO3, right? We're bonding hydrogen onto that. So our resulting acid does not have a prefix because we're not dealing with an IDE anion anymore. We're dealing with an ate. So no prefix, but still the suffix of -ic. So if we bond hydrogen to carbonate, it becomes carbonic acid. If, for example, our polyatomic was nitrate, it would become nitric acid when we bonded on a hydrogen to it, okay? If our anion is a polyatomic that ends with ITE, like, for example, phosphite or potentially nitrite, like that, we're going to see no prefix and a suffix of OUS. So this resulting acid from phosphite becomes phosphorus acid. And then nitrite would become nitrous acid. Okay, so again, a lot of stuff to remember, but we're seeing a similar pattern to the charges that we saw earlier with those IC and OUS endings. And because that pattern here, if you're seeing between the two polyatomics a suffix of IC, there's probably more oxygens there. And if you're seeing OUS, there's probably less oxygens there. So you have to pay attention to what you're looking at. Now, next, we're going to go ahead and start naming hydrates and binary covalent compounds. So again, a lot of things to go ahead and pay attention to. Right now, we're looking at two examples. We are looking at this example right here and that example right there. If you recall from general chemistry, when we're naming covalents, where there are prefixes that tell us how many. So with CO2, we would name that carbon dioxide. So if you recall this rule, if there's only one of your first, there's no prefix attached to it, but your second always is going to have a prefix denotating how many. So if this was C2O2, I would name that dicarbon dioxide, right? But since there's only one, I can just leave off that prefix. So that's the way that we already know, right? Now, there's more complicated compounds coming your way. So for example, this one here is calcium sulfate, but it has waters in it as well. And that little thing right here denotes essentially a fusion of those two things. So in the crystalline structure, you'll see both waters and calcium sulfate. So the good news for you following that is that there's not going to be a whole lot of rules that I'm going to force you to learn for these, but I just want you to remember that if you see waters attached to another compound, you're going to throw a prefix in front of the word hydrate to tell me how many. So if this was a 5, you would call that pentahydrate. If it was an 8, you'd call it octahydrate, and so on and so forth. But that's really, I just bring this up because you're going to see it. And then for this down here, let's say we have nitrogen and oxygen. If there is an instance where the prefix that you are trying to put on to that nonmetal kind of has two vowels next to each other, you're going to end up dropping one of them. So instead of tetraoxide, it would become tetroxide, and you would drop the A. Next, we're going to break into the things that you have not seen before. So you have not ever had to name or draw alkanes, alkenes, and alkynes, all of which are hydrocarbons. So hydrocarbons, all that that means is that the compound contains carbons and hydrogens. That's all that the hydrocarbon term means. There are different kinds of hydrocarbons. Alkanes is a specific kind of hydrocarbon, and it means that that hydrocarbon is saturated with hydrogen. Okay, so looking at saturation, it basically means that every carbon is bonded to as many hydrogens as it can possibly be. Okay, so with this one here, we have 1, 2, 3, 4 carbons, and there's no double bonds whatsoever. So if you see a long chain of carbons with absolutely no double bonds, you're probably looking at an alkane. The root of that name is going to tell you how many carbons are present. So in this example up here, again, we have 1, 2, 3, 4 carbons. And so we're looking at a root of but, B-U-T. And since there's no double bonds, we're going to name that particular compound butane. Okay, so if I were to give you the name butane and ask you to come up with formula for butane, in that case, you would refer to this bit of information right here. So that prefix but means, hey, I have 4 carbons in that compound. And to figure out how many hydrogens you have without drawing it, you can just use this little formula. H sub 2 times 4 plus 2. And so if we were to simplify that, we'd end up with C4H 8 plus 2, which gives you 10, right? So if we were to go up and count these hydrogens in this picture, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at that. Our formula led us to the right place. Okay, so that's alkanes. Next on the agenda, we have alkenes with an ENE at the end of it. So that suffix means that there is a double bond somewhere in that hydrocarbon. Okay, so we're still dealing with hydrocarbons. It just means there's a hydrocarbon with a double bond, meaning that that compound is not entirely saturated with hydrogens. Okay, So this right here on the left-hand side, this compound, there's 2 carbons there. So if I were to go back and consult my chart, 2 carbons means F, ETH. So our root for this is F. And since there's a double bond in the middle, we have that ENE ending, meaning that it's Fe. Okay. So again, if I were to give you ethene and expect you to come up with a formula, you would consult this bit of information. Because of the prefix F, we're looking at C2, and H is just 2 times how many carbons there are. In this case, 2 times 2 is 4. And lo and behold, 1, 2, 3, 4. Okay. Next, we have alkynes with a Y, and that YNE is going to mean that there is a triple bond somewhere in that hydrocarbon. So we see it right over here. We see it right over there. And does it matter where that triple bond is? No. If there's a triple bond present, it's an alkyne. Okay. So if I were to name this, again, I would have to count how many carbons I have. 1, 2, 3, 4. And if we were to go back and consult our chart, we would figure out that our root is bute, again, for 4. And there's a triple bond there, so we're going to put a YNE on the end of it. If we wanted to do the opposite, we would look at our prefix, figure out that that means C4, and we would use this bit of the formula to figure out how many hydrogens there are. In this case, H sub 2 times 4 minus 2. And so that's 2 times 4 is 8, minus 2 is 6, making our final C4H6. And let's count our picture to see if we're right. 1, 2, 3, 4, 5, 6. So that's naming and going towards the formula for alkanes, alkenes, and alkynes. But I do have some more information for you. So we are going to touch on this in a bit in unit 1, but I did want to mention empirical versus molecular formula. Empirical is essentially the reduced form of any formula. So if I had glucose, for example, which is C6H12O6, its empirical formula would be C1H2O1 because there's twice as many hydrogens as the others. So it basically is, again, just a reduced form. Not going to spend a lot of time on that right now, but we will touch on it later, so I wanted to mention it. Our structural formula is going to be slightly different than what you may or may not be used to seeing. So you're probably used to seeing structural formulas like this. If we drew it Lewis style, we would be drawing the electrons out. We could also draw a condensed formula for this particular thing in kind of a shorthand, but that's longer than the condensed formula. So let me explain how those things relate to one another. We have our structural formula for propane, propane being 3 carbons and 8 hydrogens. So on the left, we see CH3. In the middle, we see CH2. And on the right, we see CH3. So that's exactly what our condensed formula looks like. CH3, CH2, CH3. And why we do that is to kind of indicate how that molecule is going to look if we were to draw it out, but without drawing it out. So if I looked at this, I'd be like, oh, okay, CH3 bonded to CH2 bonded to CH3, rather than trying to mess with where exactly my hydrogens are. But another way that you can draw this is like this, which is a line diagram. So this is a form of organic chemistry notation. And it's something that you might see in this class, which is why I'm even teaching it to you in the first place. But if you see a line diagram, I want you to realize that each point on a line diagram represents a carbon. So this, again, over here is the form of molecule that you're used to seeing, but it means the same thing as the one down here. So there's 3 carbons here, 3 carbons here, because there's 3 points on that line. The hydrogens are not pictured, they are implied. But because of how carbon bonds, we know that carbon can bond 4 times. I'm seeing carbon bonded to another carbon, so that's one of its bonds taken care of. And I know that 3 hydrogens have to be attached to this one because it can bond a total of 4 times. This one in the middle, this carbon here, is bonded to 2 other carbons. So it has 2 spaces left to bond. And then the one on the right is bonded to 1 other carbon. So it has 3 open spaces for bonding. So that's how you would interpret a line diagram. Okay, so naming chains and branches is going to come next, okay? So organic chem nomenclature gets very, very complex very quickly. So let's break these names apart into their roots. So I'm going to draw a box around this right here, the tail end of this name. Heptane, that prefix hept means 7, and ane means that there's no double bonds. So the first thing that I'm going to do is I'm going to draw a line diagram with 7 carbons. I'm going to go 1, 2, 3, 4, 5, 6, 7. And let's check to make sure I didn't screw that up. 1, 2, 3, 4, 5, 6, 7. We're good. Now, let's go here to this next part. We have 4-methyl. That means that there is a methyl group on carbon number 4. So let's number our carbons real quick. 1, 2, 3, 4, 5, 6, 7. So on carbon number 4, which is this one, there is a methyl group, and methyl means 1 carbon. That YL just means it's not part of the main chain. So we would draw a line going off of there. That's a methyl group attached to carbon 4. Now, looking at this, it says 3-ethyl. Ethyl means 2 carbons. So there's a 2 carbon side group attached to the 3rd carbon in the main chain. So I might draw that like this. So our final compound looks like this. And that is how we interpret that name. Again, I know that this looks very complex, but if you break it apart, it becomes much easier. Okay, so let's switch colors. Now I have 4-propyl 1-nonene. Okay, so a few different pieces to this. Once again, circling our main chain because it's the last part. Nonene. That means that there are 9 carbons and we have a double bond on there. So the first thing that I'm going to do is I'm going to draw a chain of 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, there are a bunch of places that it's possible to have a double bond, but look what this number is. It's 1. So if I'm numbering my carbons from left to right, that means that the double bond is attached to the first carbon. That's what that 1 means. Now, our next part, we have 4-propyl. 4-propyl. So if we were to consult our chart, we would find that propyl groups have 3 carbons in them. And this 4 here means it's attached to carbon number 4. So we go to our chain and we count 1, 2, 3, 4. And we go, okay, well, I'm going to have a chain of 3 carbons attached to that. So 1, 2, 3. And that is my propyl group attached to carbon number 4. So this right here, sorry, I cut off part of the compound, but that would be our final answer. Now, when we're interpreting our line diagrams, I'm going to reiterate this because it's super important. Nobody wants to draw out this all of the time. It's exhausting. That's why this form exists. So one very helpful thing to know when you're drawing these is that carbon can bond up to 4 times, nitrogen can bond up to 3 times, oxygen can bond twice, and hydrogen can bond 1 time. When you draw your line diagrams, hydrogens are implied. We do not draw them, but we draw everything else. So if there's a nitrogen attached to a hydrocarbon or an oxygen or whatever, we would draw that in. It's only hydrogens that are not ever pictured. So if I were to ask you to go from the hydrocarbon to the name, which we'll practice a little bit, but that's not going to be a huge ask most of the time in this class, you would have to find the longest continuous chain. So say the longest chain in any particular hydrocarbon was 9 carbons long. So you would name that non something. Select your proper root, in this case, non again. Then you would name the suffix according to if there's any double bonds or triple bonds or not. So if there's no double bonds or triple bonds, you're going to give it a suffix "-ane". If there is a double bond, it would be "-ene", and if there's a triple bond, it would be "-ine". If it's in a ring, you're going to add cyclo to the beginning. So if we have hexane, that's 1, 2, 3, 4, 5, 6, that's hexane. But if it looks like this in a ring shape, that would be cyclohexane because it's formed a ring. If there's a branch coming off of the main chain, then that branch has a suffix of YL. So this is a methyl branch. If it was 2 carbons, it would be ethyl with a YL. You're going to alphabetize those branches and you're going to specify where that branch takes place. So if it came off of carbon number 2, you would write 2-methyl. If it came off of the 4th one, you would write 4-methyl, and so on and so forth. Okay. So, example problems. If we count these carbons, we go 1, 2, 3, 4, 5. That's 5 carbons. So we know that the prefix "-hent" is necessary. There are no double bonds, so we would name it "pentane". There are no side groups, so we do not need any numbers or anything else attached to that. Cool. For this one over here, we number our carbons: 1, 2, 3, 4, 5, 6, 7, 8. So that's oct. There is a triple bond in there, so we would name it octyne. Okay. This one here on the bottom left, we get to number our carbons. So 1, 2, 3, 4, 5, 6, 7. One thing you want to be careful to when you get branching groups like this is you want to make sure that your longest chain doesn't bend off in a weird direction. So if I were to name this 1, 2, 3, 4, 5, 6, that chain is not longer than this one. So that means that these two are a side group. If this chain was longer, that would be your main chain. Now, so we have 7 as our main chain. So we get hept. There are no double bonds. So we have ane, but we do have a side group, and there's 1, 2 carbons in that side group, and it is attached to carbon number 4. So instead of just heptane, we would name it 4-ethyl, because there's 2 carbons, dash heptane. And now this one over here, last but not least, we count our main chain: 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be non. There's no double bonds. So again, that's an ane suffix. We have 2 side groups here. We have one right here and one right here. This one has 2 carbons. This one has 1, 2, 3 carbons. So we have a propyl group and an ethyl group. Okay, so let's number our main chain: 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we have a couple of things to pay attention to. So I'm going to switch colors. Oh, that's a bad color. There we go. We have an ethyl group, which alphabetically comes before propyl. So ethyl is going to be listed first in our final name. So we have 6-ethyl, comma, 4-propyl dash nonane. So as you can see, this gets pretty long pretty fast, but I'm almost never past this particular unit going to ask you to come up with a name, because it's more important for you to be able to come up with a formula from the name. This is for your reference. I do not expect you to memorize these, but if you see this name, I want you to go back and reference this. So if you see ketones, or if you see carboxylic acids, or if you see something in one of the homeworks, in one of the assignments, in one of the AP questions, I want you to be able to have a reference that'll tell you what that means. So that's all that this is for. And then the last sample problem is something else that, again, you might see, but I'm not going to expect you to memorize at all. And that is cis versus trans. So we have 2-butene. Butene, meaning that there are 4 carbons. So 1, 2, 3, 4, 1, 2, 3, 4. And attached to the second carbon is going to be a double bond. And we know that because there is a ENE ending and it has a little 2 in front of it. So if we were to draw this out longhand, we could say, we could do it like this. And attached to these 2 carbons, there is this on either side. So there's 4 carbons total. And then there's 1, 2, 3 hydrogens. And on this side, hydrogen, hydrogen, hydrogen. But there's 1 hydrogen here as well, and there's 1 hydrogen there. So if a molecule is something called cis, that means that this and this carbon are going to be pointing in the same direction. So that means that on the whole, the molecule is going to look like this. If it is trans, on the other hand, that means that our carbons on either end are going to be pointing in different directions. So you would notice something like this instead, which looks a little bit more like what we drew up here. Okay. So again, I don't expect you to memorize this at all. I just want you to have a reference for yourself. That's all. So now, once you come to class, you should have cheat sheets for all of this to go ahead and reference. I hope this was helpful for you. If you have questions about any of this, please come to me, you guys. I know that this is a lot at once. Trust me, I know that. It felt like a lot to me when I was learning it. So if you need help, please come to me.